So one of the things about proportionalities is that you can make them into equations by inserting a constant. So one of the things they found from the empirical gas laws is that pressure times volume is always proportional to moles times temperature. Now, it turns out that there's a single constant that makes this equation true for all gases. And so they gave it a special symbol R, and it's actually known as the ideal gas law constant. And gases that behave like we talked about at the very beginning in kinetic molecular theories, that have no attraction, move in straight lines, kinetic energy is proportional to temperature, uh, those gases obey this equation, the ideal gas law. So what we did is we took this value and just said this. Well, let's go and make it PV is equal to N times R times T. And I don't know why they put the R in the middle instead of at the end, like, or at the beginning like they do for lots of constants, but this is how they chose to do it. And so this equation is what we can use to calculate the pressure of a gas uh, without like knowing what a previous state is. If you just want to know what the pressure of a gas is, all you need to know is three other variables: the volume, the moles, and the temperature. The value for R is this one here. This is the one that's generally used in your book. And it also has an energy unit one that we don't use in this class, but just so you know, there's lots of different versions of R. And the one that you want has liters, atmospheres, moles, and Kelvin in it. Okay, so you have to really pay attention to these units. Now, when you use this equation, you don't have to be that careful as long as all the units in your values match the units in R. All right? So make sure, make a little note here, make sure you match units with R. This is one of those situations where you really do have to spend time writing all your units out. Okay, so it says a cylinder, right, contains 1.5 moles of gas, has a pressure of 35 psi at 26.5 degrees Celsius. What is the volume of the container, right? So this is not like the previous problems where you say you have a pressure, what's the pressure when it's this, when we make these changes. So this is just asking you for the pressure. So I'm going to say PV, or sorry, is asking you for the volume, is equal to nRT, right? And I need to solve this for the volume. So I go V is equal to nRT over P. So now, I always tell people to do this. Write the variables down. I have N, R, not really a variable, it's a constant, and T, and I have P, right? And then the first thing you want to do is write out the value for R. So it's 0.0821, and that's liters times, I almost spelled liters, times atmosphere, divided by moles times Kelvin. And really, you don't really have to write the value here. What's really important is that you have the units here. So you notice it says 1.5 mole, so I'm good, 1.5 mole here. It says 26.5 degrees Celsius, but this says Kelvin, right? So that means I have to convert it over. So I'm going to go 26.5, sorry, lost my place. 26.5 degrees Celsius, and we always just add 273 to it, so that'll be my temperature. Let me move my pressure down just a little bit. And then we're going to go pressure, that's going to be 299.5 Kelvin. And my pressure is 35 psi, right? So then that's 35 psi, and I have to ask myself, does that match the pressure units in R? Well, R, right, is an atmosphere, so this has to be converted over. So I'll say, well, I know it's 14.7 psi for every 1 atmosphere, like that. And so now I can plug the values in. I can calculate this and plug it in. So let me go ahead and calculate that value. So 35 divided by 14.7. That's going to be 2.381 atmospheres, like that. And I really only have 2 sig figs, so I'll mark it there. And now I can plug the values in. So I have N, which is 1.5. I have R, which is 0.0821 liters times atmosphere. I keep doing that. Liters times atmosphere for every mole times Kelvin. And I got to move this because I just ran out of space. And then temperature in Kelvin, 299.5. And then divided by 2.381 atmospheres. Again, I only have 2 sig figs here. I only have 2 sig figs here. R is only 3 sig figs when we're doing these calculations. There are more significant figures if you need them, but typically for this class you don't need more than that. And I do all the problem calculations based on that R value. Okay, so I'm going to grab my calculator again. I'm going to do the calculation. So I go 1.5 times 0.0821 times 299.5 and then divided by 2.381. Make sure I got all the numbers in there, right? Hit equals, and that becomes 15.49 atmospheres, or liters, sorry. With 2 sig figs, so this will come out to be 15 liters, like that. And the reason I wrote these digits out is because just because the 4 would round up to a 5 doesn't mean you round the 15 up to a 6, right? You don't make it 16. This is still a 4, so this will be rounded down. Now, just to show you how this works, because you notice I sort of came up with liters kind of magically, right? The moles will cancel here, the Kelvin will cancel here, the atmospheres will cancel here, and then I end up with the volume in liters. Now, here's one of the important things to recognize. As long as you match these units over here, the volume unit here is the volume unit that it'll come out with, and everything else will cancel out. All the other variables will cancel out. Let's do one more. And we're going to say, what is the volume of a mole of gas at STP? So again, we have to pull up, what does STP mean, right? It's standard temperature and pressure, 1 and 0, right? So it's 1 atmosphere and 0 degrees Celsius. That's also 273 Kelvin, just it's easy to remember that way. Now, and by the way, when I say 1 and 0, it's easy to remember. You should probably be pretty certain that it's not 0 atmospheres and 1 degree Celsius, because 0 atmosphere is not a gas, right? There's no gas present. So 1 and 0 is pretty easy to remember that way. So we're going to do the volume. So volume is equal to, and then I need all my variables, right? So I have P, V is what I'm solving for. I'll just write it. N, R, and T like this. P is 1 atmosphere. Volume is what I'm solving for. N, 1, right? And this is an exact 1 mole. And R is, again, 0.021 liters times atmospheres per mole times Kelvin. And temperature's 273 Kelvin. And I've matched all my units, so all I really have left to do is plug these things in. So I'm solving the ideal gas law for volume. Remember, it's PV is equal to nRT. So I'm solving it by just dividing by P on both sides. And so I'll get nRT like that. And I can plug in 1 atmosphere times 0.0821 liters times atmospheres per mole times Kelvin, and then 273. And my pressure is 1 atmosphere. And I'll go ahead and run the calculation. Actually, I just know this one is 22.4, right? Because this is 3 sig figs. It's 22.4 liters. And I know it's liters because I did everything else in the units I was supposed to, right? And so I know it all cancels out. It gives me liters at the end. So there's a lot of applications, and that's actually what we're going to head into next. But one of the things I wanted to point out is all these problems are essentially done the same way. You write out the equation, you write out all your variables like I did here, or like I did here, I included every single one of them in the equation. And then I read through the problem and I wrote those things out. First thing I did though is I wrote R and the units for R. That's the most important thing. And then I made sure all the units matched. I solved my equation for the thing I was looking for, and then I plugged in numbers, right? So first thing I did, again, was I wrote this out. Second thing I did was this. This is the third thing. And this is the fourth thing right here. So basically that's the order. Identify the variables, solve the equation, that's steps 2 and 3, and then plug the values in, and then calculate.